All right, so welcome back. So the last class, we presented the equivalent circuit model of our synchronous generator. In this case, it's a generator, right? We're going to treat it as a generator primarily. You do have some synchronous motors. Those are called synchronous condensers. We'll look at that a little bit later on. Then they weren't that common, but they are becoming more common. I worked on a project, it's been a couple years, but it's a project in New Hampshire where they were putting in a 50 MVA synchronous condenser at a substation called Huckins Hill, New Hampshire. And the idea is that with all this DG, distributed generation or distributed energy resources, you don't have really strong systems in terms of being able to provide fault current. And so when a fault occurs on a system, these synchronous condensers can actually help maintain the system grid, meaning the voltage, and then you can actually detect the fault. So the synchronous condenser is really there just for fault analysis. If you were to go over at Pasadumke, they have something called DVARs, dynamic var compensators, which are made by American superconductors. I don't know how they got in business, but it uses some semiconductor devices and power electronics. And I think they're rated for 600 kVA. So they have 2 or 3. And the whole idea is to maintain the voltage during a fault. So I don't know how PSNH, which is now I think part of Eversource, decided let's go ahead and put these synchronous condensers because it was expensive and they always rotate, right? That's the whole thing about a synchronous machine. Unless it's running at synchronous speed, it's not doing anything. So it's got to spin at no load, right? It's just a spinning machine. So it's got some losses. So it's got some kilowatt losses. And I would have thought cat banks would have been a better way to go, but who knows? I'm not a systems operations person, so I don't know all the specifics of there. But we're going to take our synchronous generator equivalent circuit or synchronous machine equivalent circuit, and we are going to figure out how to calculate these parameters. That's what we're going to do today. All right. So we did allude to it a little bit when we looked at, oh, how come this is not going to the next, well, there we go. What's that? Yeah, that was just a reminder about making sure I unmuted myself, which I hopefully have already done so. This is going green, so that's always a good sign. So how do we determine these parameters? Well, in transformers, we did open and no load tests and load loss tests, sometimes called open circuit and short circuit tests. That's pretty much all the testing that we can do with any electrical piece of equipment. Some people will tell you to run frequency response and do all these different things. The problem with doing things at frequencies is as you sweep the frequency along, are you actually operating the equipment at whatever frequency you specify? So you don't always have really good results when you do things at off nominal frequencies. So we're going to do very similar approaches, but we're going to add one additional test. And we're going to call something the DC test. We'll add that part of it into our electric machines to go ahead and do that. Now, you notice, though, and if you recall, when we looked at our previous results, when we looked at Northfield Mountain, oh, I guess it's not there. I thought I had opened it up already, but maybe not. So when we looked at a generator, and we actually saw there are a bunch of curves that were pretty useful for us. So the first one's the B curve. We'll look at that when we get to synchronous machines. But this is the saturation curve or saturation characteristic. And what we mentioned is this curve, actually, we're going to be able to use this to actually calculate our value of X sub S, our synchronous reactance. And that's the only thing you can calculate from our tests. You can't calculate anything else but my synchronous reactance. Remember the curves that we have. If you look over here, you have a no load curve. That's important to us. Another way to say no load curve is an open circuit curve. And then if you also scroll down a little bit, what's curve number 2? Curve number 2 is the short circuit current line. It's odd. Why would you want a short circuit current line? Any thoughts?
Maybe what the town. When did the fish of the time?
Not that intersection per se. But remember, this is what our excitation, remember that we adjust the field current and we're going to get a supposed voltage over here. This is our excitation. This is the output voltage that we're going to get. We only can measure this voltage if the voltage drop of the system is 0. So by doing the open circuit test, that does allow us to get our voltage here, right? So we can get the voltage there. The problem is how do we calculate what this impedance is going to be if we have no current flow? Isn't Z equal to V divided by I? So we got to get I, but the moment we get I, we no longer have F or EF, correct? So here's the thing. If we put a short circuit over here and we run it up to rated value, whatever the power output would be, what we get is we measure a current here, right? We have a current here, and then we don't know what this voltage is. We can't measure it because we've got these internal voltage drops. But what we can do is we can build a curve. So we're going to sit there and run our machine with an open circuit. Then we're going to put in 1 amp of excitation current. Then 2 amps, 3 amps, 4 amps, all the way up until we get this maximum value.
What's up?
Then we get our open.
Half paying attention to a Zoom class, and then I gotta.
Yeah, we have technology. We can fix it. So we get this curve, and then we're going to go back and redo the test. But now we're going to put a short circuit on the terminal, and all 3 phases are going to be shorted together. And we're going to monitor that current, not the voltage, because this voltage should be 0. And we're going to do the same thing. Start at 1 amp, 2 amps, 3 amps, 4 amps, all the way until we get to, basically the maximum current that the machine can provide. And we're going to plot that. And the way that we calculate this internal impedance is at a value of I sub C or I sub EXC. So if you look over here at this level of excitation, I can see that I get a point on my short circuit characteristic. That gives me a current. Then I go to my next curve and I get a voltage. So my impedance Z at an I excitation is going to be equal to V open circuit at that excitation divided by I short circuit at that excitation. That's how you solve for that parameter Z. You're going to get the impedance. Okay? So that's what we're doing with our 2 tests.
So you're using the two.
I got to use the 2 plots. Yep. Yeah, I can't get any parameter by itself with just 1 test because I have no way of knowing what the voltage and the current is. This voltage over here is inaccessible to me. It's across the windings. That's the voltage that's impressed across the windings. Then I get voltage drops over here anytime I draw any current. So the only way that I can get an impedance is I have a voltage and a current. So I can't draw a current and get the accurate voltage. I can always get the current, but I can't get the voltage. So if I need both, the only way I can do it is to pull those off the same point on the curve.
So you're getting the first red line and the second because the two.
Well, look at my curve, right? That's the open circuit characteristic. And this is the short circuit characteristic. So that is going to display current. And one's going to be voltage. Yep. And if you look closely, that's why this curve here either says no load voltage, short circuit current, or the load characteristic. It has that information. All right. So it provides it that information. Otherwise, you'd have to have separate graphs where you couldn't overlay them. So putting them on the same graph makes it really useful. You can pull that data out.
So from any point you take load from Z will be the same.
Any point, as long as you are not saturated. So this is unsaturated, and you can see up until about here, the voltage and the current are about the same. When I get over here, now I'm saturated, right? So now I'm in a different region essentially. So I'd have to use different values. Okay. All right, so let's get back over here. Now, the one thing that we haven't talked about is the DC test. Well, the DC test is necessary because with your short circuit and open circuit tests, you only get the impedance Z. You don't know X and you don't know R. But once you know one of those parameters, R, then you can pull out X. So we'll do the DC test. And this is our DC test. Wait a minute. That says DC. I'm not sure why the figure. Oh, sorry. Okay. So let's skip over to the DC test. So in the DC test, you're basically, all you're doing is the generator is turned off and you're walking up to the machine and you're connecting a DC power source to it. But remember what we have, the machine is going to be connected internally. Like that, right? So this is on the neutral side. So unless you can actually measure the neutral side and put DC over here, more likely than not, you're actually going to be only able to measure the test on one side. So if this is a Y connected machine, I have my resistor and my inductor here. And if I put a DC test over here, what ends up happening over a long enough period of time? What happens to my inductor? Yeah, these just go away, right? Those inductors go away. And in a Y connected machine, I have RA, I have RA, and I have my DC. So if I measure VDC and divide it by IDC, I have 2 times RA, right? Everybody see that? I just got 2 in series with each other. Now, if the machine is connected in delta, and I'm going to go ahead and throw away the inductors because in DC, right, they're not part of the picture. And I only have a DC source, so I'm only going to connect, I only have 2 wires. I have a plus and a minus of DC. I don't have 3 wires, I only have 2. So what is VDC divided by IDC equal to? What does that equal? It's equal to RA? Yes, sir? RDC, that's the RDC, but looking at the schematic, what is it equal to?
The equivalent of yeah. The equivalent, the all in 3 times RA. No,
3 times RA?
No, but then the equivalent of all.
I have this resistor here, right? Can see that one. But don't I also have there's a wire over here. Well, where does that go? It's not connected. It's an open circuit. So whether that wire exists there or not, it's irrelevant. So VDC divided by IDC is equal to RA in parallel with 2RA, isn't it? And product over sum. RA plus 2 RA, which is equal to 2/3 RA. So that's where these equations come from. Anybody have an issue? I said it's 2/3 RA versus 3/2. Anybody think I made a mistake? Yeah, because I said RDC is equal to 2/3 RA, right? So that means RA is equal to 3/2 RDC. I don't really care what RDC is. I really care what RA is. So if you have a delta or Y circuit, you have to configure, how do I calculate what my RA is? Okay, that's the RA. Now I'm running the open circuit test and I get my open circuit characteristic curve. I get this curve right here. Curve number 1. That's what the open circuit curve gives me. And it even tells you the no load voltage curve. Remember when we did transformer tests, we did the open circuit and short circuit tests on a transformer. But then when we looked at the transformer data sheets, the test report, we saw it was the load loss test and the no load loss test. You can see no load voltage curve. It's the same thing. They just call it no load voltage curve. That's our short circuit. How do you do this test? You run it at rated speed with no load, with a completely open circuit. Okay, and then you just measure the voltages. What are the voltages? And these voltages here normally are going to be line-to-line voltages. So in this case, it's a generator. It's 13.8 kV. The voltage that you're going to be measuring is 13.8 kV. I know it says 1.5 and 1, but that's basically a ratio voltage. So if you actually did your calculations correctly, you would see that you'd end up with 13.8 kV. That's the open circuit test. Okay. Do the short circuit test. The only difference is I'm going to short all 3 phases. Since it's a balanced system, I really only need to have 1 ammeter because the other 3 should be the same. And I'm only looking for the magnitude of current, which is good because the ammeter can only give me the magnitude of current. I don't have a voltage to reference, so how could I get anything but a magnitude of current? Right, does everybody know if you want to get a phase angle of a voltage and of a current, you need to have a reference for it. So you can't just stick a meter on there without having another reference point. That's normally why we pick voltage as a reference, and then current, we either say it's leading or lagging that voltage by whatever. So we would need that value. But since the voltage here is always going to be 0 volts, we don't have a voltage reference, so we can only get the magnitude of current. And just like in the open circuit test, where we monkeyed with our excitation current, we do the same thing for the short circuit test, and we get our short circuit curve over here. Now we have 2 curves, and now we have all kinds of points to be able to calculate impedance. Here's kind of a zoomed in look with that, to sort of show you the specifics. So we have one other thing, which is called the air gap line. And the air gap line, you can see it intersects the open circuit characteristic without peeling off. So what do you think, or what do you know about the open circuit, the air gap line? Got a constant slope. What else? The smallest? What do you mean? Well, there's no current there. That's excitation current for a certain voltage. It just shows you what the voltage would be if you didn't saturate it. So if the magnetic material didn't saturate, it would exactly follow the air gap line. So the air gap line is not something that you actually measure. It's something that you calculate. Once you get beyond the open circuit characteristic, so you find the slope of the line here. And if you want to find any value of what that voltage would be unsaturated, you would use the air gap line. But our open circuit characteristic is what we measure. We get a point there. We also get a point on the short circuit characteristic. And these are at two distinct values of excitation current, field current. And then we can see that off of our open circuit characteristic, we have a voltage. We call it VA. And our short circuit characteristic, we have the same thing. We have a voltage, but then we also have a current. And notice these are on different axes, right? This is a three-axis plot. So our current that we're going to calculate is from here. So to solve for our Z, and this is unsaturated, this is our ZS unsaturated, we go magnitude RA squared plus XS squared, square rooted. Once we have the DC test, then we can pull out XS unsaturated. Okay? Makes sense. So all I'm looking for is if I want to be where I want to get what the synchronous reactance is going to be when it's unsaturated. So I'm going to pick any point on the curve that the open circuit characteristic is linear. So I'm picking this point right here. Okay, that's non-saturated. That gives me a voltage, gives me a magnitude of a voltage. Now, at that same current, at that same excitation current, not a different one, but the same one, I'm going to get a short circuit current off that curve right there that I read from this value. To actually calculate the Z, I go V divided by I, and those are both unsaturated values. So that's my unsaturated value. And this is my unsaturated value. And what I said, if you remember originally, I said Z at an excitation current is equal to V at IXC divided by I at IEXC. So I just need to make sure that I'm grabbing those at the exact same excitation current, field current. I can do the same thing for when I'm saturated, when I'm running at rated voltage. Doesn't have to be rated voltage, but that'll change a little bit. And you can see, grab a rated voltage, take that off that curve. That's going to give me a corresponding excitation current. Once I have that, then I can pull that line off my short circuit characteristic curve, and that gives me my value of I. So then I have two values of Z. I have Z saturated and Z unsaturated. Got two different values. Now, everybody thinks I'm BSing them, right? Well, let's see. Let's look at some real data. So remember our friends in Millinocket that have that generator that I keep bringing up a fair amount? Oops. Let's go and look at that generator again, because we saw XD, XQ, all those different things. Whoops, this is the wrong class. Sorry. Look down at your values for your motor parameters. Or I don't know why they call them motor parameters. It technically should be machine parameters, right? Because it doesn't matter. What do you notice about the machine parameters? There's two per reactance, isn't there? Look at XD, 0.75 versus 0.86. Why is that? Why is there two? It actually tells you. One's the saturated value, one's the unsaturated value. So this .75. XD unsaturated is 0.86. What's that? Says it right here.
Why did they give us the, like, the-
Well, because if you're trying to do modeling of your generator, you're going to put in your impedance or in your curves, you're going to put either saturated or unsaturated values, and sometimes you put both in your data sheets. So you would include perhaps both parameters. Because the hard part is like when you're running these things, you're trying to calculate the impedance, and the impedance can vary. And so when you're operating here, you normally just assume sort of a middle of the road number, because otherwise you have to come up with a nonlinear curve, and it makes things much more complicated to do it. You can model it, but the problem is now you have to do a small signal analysis, or you actually have to have a lookup curve, which is, hey, my excitation current's this is what the voltage needs to be, so you can make it more challenging for you. Okay? That's how you're going to do some tests. All right, so here's your equivalent phasor diagram or circuit and a phasor diagram. We combine everything into one value X of S, and we include our armature reactance as shown, and then we have a phasor diagram shown here. So here's our leading or lagging current. Lagging current because it lags the voltage. Here's my voltage drop IARA because of the fact that it's in phase, right? There's no phase shift through the voltage drop across the resistor. And then I have to phase shift at 90 degrees to get to that. And the sum of those voltage drops become my EF. In many cases, you can just ignore RA. It's so small, you can ignore it. Let's see if that is okay for these parameters. Let's see, this was 0.75 and 0.86. How does that compare? It's 100th of the value of XD. So you can calculate it, but it probably is not going to change your result all that much. The other thing to notice, does RA have a saturated or unsaturated value? Do you see two values for RA? Why not? Because RA is just coil resistance. It doesn't need magnetic energy, right? The magnetic energy can be what it needs to be. The resistance is just the resistance. So there is no saturated or unsaturated resistance. It's only reactance.
in the calculation, yeah, like with Z,
You can't in the calculation
yeah,
because how did I determine RA? From the DC test. I didn't even look at the two curves. The only thing that changes when I do saturated or unsaturated is my value of X. DC I got from DC, so it's a fixed value. It never changes. Okay. So this one is another parameter. Sometimes you see it. It's the short circuit ratio. It's hit or miss if it's been provided. If you look over here, do you see an SCR anywhere here? I see saturation factor. Rated current, service factor. Right here. See right here? So they do actually calculate what the short circuit ratio is. It's not a usually very useful parameter. It just gives you a ratio of calculating what the rated current is for voltage divided by the rated excitation current for your current. So this is a DC. This is DC. This is just based on the DC value. So you can see that those are there. One thing to be careful of when you do your homeworks, remember, this here is in DC. These are in AC. So when you calculate Z, would you calculate that? The answer, I hope, is no way, Jose. Because if we're doing AC circuit analysis, how can you divide an AC voltage by a DC current? So it's not that, it's V rated AC divided by I short circuit AC. Those have to be AC voltages. You can't divide AC and DC. And if that doesn't make sense, take a look at where my DC comes in. My DC is over here and my AC is over here. Their circuits aren't electrically connected to each other. They're completely independent from each other. So there's no way a DC current can have any impact on the impedance that you're calculating in the AC circuit. All right, let's take a look at an example. 200 kVA, 480 volts, 60 hertz pole, 4-pole machine, Y connected. So that's important. Why is Y connected important? It's important for two reasons. The first thing is it gives us our diagram, which is going to allow us to see that this 480 volts is across two phases. The actual voltage, see if I can erase that. Across the individual equivalent circuit is 480 divided by square root of 3, if that's what it's operated at. So the other thing that it needs to calculate or help us calculate is RA. What is RA equal to? RDC divided by 2. Very good. So from the open circuit test, you've got 540 volts at rated field current. That's at rated field current. And the line current is 300 amps at rated field current. Anybody have any issues? That's 540 volts. It's a 480 volt machine, but it's running at it's outputting 540 volts. Anybody have any issues with that? 60 volts higher than nominal. I don't, because that only happens if the voltage drop is equal to 0, right? And how much load is connected to the machine if the voltage drop is 0? None, which is not how you're going to run this machine, right? I only care about what the terminal voltage is going to be. That's where I connect the load. That's going to be 480 volts. The internal voltage can be higher or low, and that's perfectly fine as long as I get around 480 volts as the output. So I've got 540 volts. 300 amps may or may not be a lot of current. I don't know. I'd have to calculate it based on the machine rating. And I have a DC voltage of 10 volts across any two terminals, and you measure 25 amps. The first thing we need to do is calculate the speed of rotation. This is an easy one. What's the equation for M? So 7,200 divided by, what's that equal? 1,800 RPM is the speed. Now, the next thing we need to do is we need to calculate what our values of XS and RA need to be. Well, fortunately, these are both taken at the exact same current. So we can use those values to calculate our XS and our RA. So the first thing we'll do is calculate our value of XS. What am I dividing by 1.732 here? What's the square root of 3 equal to? 1.73 whatever, right? I need to get the nominal voltage, the 540 volts. I need to drop it across one individual phase. Just like we did in three-phase transformers, when we had three-phase systems, we would have to convert that and divide that by square root of 3. So we divide 480 by the square root of 3, and then that's how we get our value. In this case, it's 540. So this voltage here is 311.8 volts. All right. Now, we can go ahead and realize that this current is 300 amps. And we can draw those on the same equivalent circuit because that's the excitation that we're going to get, right? That's at that value. So my value of Z is equal to 311.8 divided by 300 amps. That's equal to 1.04 ohms. The DC tests, we take our 10 divided by 25 and divide that by 2, and we end up with 0.2 ohms. To get the exact value of XS, our XS value is going to be equal to our Z that we just calculated, 1.04 squared, subtracting my RA, 0.2 squared, and I end up with 1.02 ohms for my X value. I said that this is X saturated. Is that correct? Could it be unsaturated? It's possible, but in most cases, when you're running at rated voltage, you're always going to be in some degree of saturation. So anytime you're running at rated field current, you would expect that rated field current is what it's going to do to drive rated load. So the voltage should be pretty high or relatively high compared to what the nominal voltage is. So that's why we call it the saturated value.
Why did you do that IDC?
Because RDC is VDC divided by IDC, and RA is equal to RDC divided by 2. I'm trying to stay a step ahead of Barzillai. He's tough though. He's really smart, works really hard. So let's do it in MATLAB. Nothing up my sleeve, right? Anything up my sleeve here? I run it. There's nothing fancy. Let's go ahead and go over to MATLAB. Just make sure there's really nothing up my sleeve. Oop, this one over here. I'll do clear and CLC. So now this is perfectly clear. So now I'm only going to run that script file. I'm going to run it to here. All right, let's go back to MATLAB and see what it says. MATLAB says my calculation for RA is 0.2, which is what we had on the slides. And I'm sorry, Barzillai, I was wrong. I said it was 1.02. I wasn't exact, 1.019. Close enough, right? So those first 11 steps is how to do those values. Okay? Questions on calculating this? Because now we can go ahead and monkey with our load. We can actually look at load, and then we can go through the process. And if we have an equivalent circuit, so now our circuit looks like this. This is EA or EF. This is J 1.02. And this is RA equals 0.2. We're going to cancel that out because we're just going to assume that, you know what, let's just call this J 1.04 and skip the value of RA just to make it a little bit easier. And here's what our system is. So now we're going to connect a load to it. And the load is going to vary based on each of those different conditions or different cases. The first case is if the current is at 100 at a 0.8 lagging power factor. Then we move to leading power factor, and then we do unity power factor. So let's go over to MATLAB. Oop. And let's check and see, do I have these correct? My X sub S is 1.04. My first case, IA is 100 at an angle of minus 0.8. See how I just put that in here? This is 100 times e to the minus j theta. And because I had 0.8, I had to convert that to take the inverse cosine. So I have that value there. This voltage, what am I doing here? I'm assuming that this voltage is fixed at 480 volts. Okay, that's what it's nominally delivering. That's what the customers are paying for. So I'm going to assume that it's running at 480 at an angle of 0. It's a good reference spot, so I'm going to pick that as my reference point. All right, so now what do I need to do? So actually, let me redraw this on whiteboard so it's a little bit easier to see. Here we go. So now my equivalent circuit looks like this. This is EA or EF. This is J 1.04. This is where my load connects. And the voltage here, it's 480 at an angle of 0. Is that correct? I thought it was 480 divided by the square root of 3, right? Because it's a Y-connected machine. So don't forget, we need to include that dividing by the square root of 3. And now our load can change. So if we want to solve for EA, EA is going to be equal to 480 over the square root of 3 at an angle of 0, plus whatever our current is, times J 1.04. The current is going to be either 100 at an angle of minus, what's cosine of, inverse cosine of point is at 36.87. I think. Those are the 3 load currents we're going to get. Once we have EA and I, then S is going to be equal to, this is where we're going to be careful, 3 EA times I, whatever the value of I is at an angle of theta, and we got to take that conjugate here. Here's where we have to be careful. The angle EA, the value EA here, this is going to have a magnitude and an angle, correct? So you need to make sure that that angle is included in your calculations. Otherwise, you're going to get really wonky results. Okay? So here is my BT. Anybody have a mistake that I made here? Isn't BT wrong?
Yeah.
How about we highlight it over here in a separate slide? Now, can you see it a little easier? I'm not doing any calculations at that part. I'm just looking in here and I'm going to see, all right, what would be the E for those cases? So you can see that here's my EA. Wait a minute, I'm doing this as a, I'm doing it the other direction. Let's just fix it over here. Okay, so that's that fixed terminal. Let's do that over here. And the last one is over here. Those are my 3 values. Here's my EA. And then what I need to do is, instead of multiplying by 3, I have to multiply by this value here. Now, let's just double check. It says calculate the real and reactive power delivered in each case. if you look here, the real and reactive power delivered each case, this is delivered actually to the load and not that the machine has to consume. So let's just go ahead and do that. Same thing over here. So the difference that I'm calculating over here is what's the power being delivered to the load. That's what S lag, lead, and unity are. What I just showed you over here, whoops, on whiteboard, is this is the power. So this is the total power. And that includes the Q that is consumed internally in the machine. So you need to set up some magnetic energy in the machine. It's going to provide its own field. So that's the Q that we'll have. So let's run that. Or let's keep running it, I should say. And now, so I have my voltage. If my internal is lagging, remember how we said at 200 amps or 300 amps, that's the rated excitation current. Look what the voltage needs to be. Magnitude, 548.74 volts. And you can say, well, is that a lot or not? Well, let's take a look. That's not even multiplying it by the square root of 3. Right? I would still need to multiply this by the square root of 3 to actually get the voltage across the two, what would be the equivalent of the two. But it's usually not that useful to show that because this is just the voltage across the individual winding. So I need to crank up the excitation to 49, almost 550 volts at an angle of 8.72. Here's the power that's delivered to the load, 66 kilowatts plus J or plus 50 or so kVAR. Now, if I do it with a leading power factor, look how small the voltage gets. It drops by over 100 volts. And that's because I'm getting some magnetic energy from the load that's connected to it. And the direction of P, we talked about this before. So P, if you remember a box, if it's a load, P is in. If it's a generator, P is out. But Q can go in either direction. And the way that we dictate if P is in or out is by looking at the angle. That's P. So P flows from theta 1 to theta 2. If theta 1, whoops. If theta 1 is greater than theta 2. Q flows in this direction, but it's based on the magnitude of the voltage. So Q flows in this direction if the magnitude of V1 is greater than the magnitude of V2. That's typically how it is for systems with fairly high X over R ratios. And we can see that here, that our voltage dropped a lot. Okay? So it drops significantly. And then lastly, our EA, this is at unity power factor. You can see that it's kind of in the middle. It's not at the peak and it's not at that low value. So it's kind of in the middle, but closer to that unity, that nominal value that we have. Okay. Let's see, where am I? Questions on calculating these parameters? Clear as can be? Yes, sir.
The open circuit and short circuit test slide where we have those two circuits, are those like what we should be looking at one for?
Yeah, because this is the DC side, and this shows you this is measuring the voltage in the open circuit, and this is measuring the AC current in the short circuit. When I looked at it quickly, I just thought that this was the DC, so I got confused, but then it actually, so those are correct.
Gotcha.
Questions? Yes, sir.
One of the last slides, you got I, you just kind of got rid of the angle on.
There is no angle on the current. There's only magnitudes because remember when we did our transformer tests, we could measure some parameters, V and I, but we couldn't get angles if we just measured V and I. So we had to calculate P to be able to do that. In here, you can't calculate P because how do you calculate P when the voltage is 0? Can't do it. How can you calculate P if the current's 0? Can't do it. So that's what makes it very difficult to do that. And where is the input power into this machine? The guy shoveling coal in the boiler, right? Because this is a generator, so it's converting mechanical energy, thermal energy, I should say in that case, into electrical energy. So the applied power is not even electrical. It's a turbine that's spinning it or pushing it, or a reciprocating engine. So there is no input power that we can measure. That's why getting these data points is much harder to do that. Yes, sir.
On the graph here, it's the IF DC or AC.
Is the IF? It's always DC. In a synchronous machine, your field has to be excited by DC.
But then you said that we shouldn't your big expression and the new IF expression is also DC, right?
Say that again?
Z to be over I, right?
Yeah,
So that I, which I is it?
it's got to be AC. That's what we talked about, right? If you look at, where's the slide? I have it. I'm just trying to find.
It was on the slide.
Was it on the slide? I missed it.
In the graph. Then you go down to the
Yeah. So this is the short circuit ratio, but over here I said when you're calculating Z, right? Z is actually the AC values.
so then now where is the AC value?
Right here,
Yeah, where do you
Current?
where do you get the AC value of the current?
from the short circuit characteristic. That's why you need that second curve. I mean, that second Y axis. This is the 3-axis curve, right? You have field current on the bottom, you have voltage on the left, and current on the right. Yep. In the Northfield Mountain, not Northfield Mountain. Yeah, Northfield Mountain. Sorry, I get too many things going on. I don't know why the PDF just gets lost. But over here, there's only one axis, except there really is two, because the way that they did these units, they could put it in per unit, and there's a way to do things. It's basically percent where you can do these on the same axis. Okay. Clear-ish? That makes me happy. So incredibly happy. Why does it make me happy? Because you got 2 homework problems to do. Generator equivalent circuit. Because I have an extra W in there, fat fingers. And if you look at the file, it's the electrical characteristics. So what I should say is calculate the saturated extra T there. That's your first one. So that's the Northfield Mountain. That's the one we've been looking at. So calculate that. And then the other homework is here, assignment number 4. which is you gotta do some calculations with an equivalent circuit, and what do you know? Some data. And I gave you some suggested problems. And this one, I even gave you something to think about, which is for this problem over here, you actually have to calculate, but I didn't give you a graph. I just gave you a bunch of parameters to work with. And these are due a week from Thursday. Why are they due a week from Thursday? Anybody want to guess? What's that? No, but why would I have them both due on Thursday and not the following week? Spring break, right? So you get them done before break and then you don't have to worry about it, so you can relax. Because we'll probably have a test when you get back from spring break. Probably, yes, that's the date. Yes, sir, Kyle?
The first, the one for the generator, so it's very easy to do this, like.
Just do this Thursday? Says it's due, oh, it's wrong one. Do you want to do this Thursday? You want to do Tuesday? This one says March 7th.
No, it will do. Yeah, like 29, yeah.
Oh, I guess, yeah, the dates don't correspond, so. So you want to do on Thursday?
Sounds like a plan.
Do you want it this day? Okay, I can swing that. Questions? Now I can go out and specify and work on synchronous generators. And again, I try to bring up a lot of curves and a lot of information that I've accumulated over the years of doing this to show, these are real world applications, right? We can see saturated and unsaturated reactances. We didn't necessarily see the saturated and unsaturated reactances for Northfield Mountain. Anybody want to guess why? Because we didn't go up enough, right? Let me go ahead, share my screen again. So if I look, let's see if I have X values. So that's generator electrical characteristics. There's some degrees C. And here you go. Direct access synchronous reactance. So guess what? You already know the answer. I'm giving you the answer. How magnanimous am I? But should show me your work, right? That's why I said calculate them, don't write them down. But the answers are right here. What? No, thank you. No, it's the same thing as the transformer stuff, right? You actually have the data in there that actually tells you the answer. So you can see saturated versus unsaturated. The other one, the other generator, it's not that big of a deal. They didn't even bother giving you the characteristics. This is a much better, more expensive generator, so they actually did way more detailed testing of it. Kind of crazy though. Think about how to actually do these tests. This is a 300 MVA generator. It's almost as big as this room. And they have to actually put it on a test stand and rotate it at whatever that speed was, 257 RPM, and put an open circuit and a short circuit on it and record that test data. So you can see why running a test is not the easiest thing to do on some of these pieces of equipment. Some of the testing thing can be millions of dollars just to test a piece of equipment. So you get the idea. All right. Any questions on anything? Feel good? Feel indifferent? Can't wait for break? Okay. Well, that's all I had unless anybody has anything else. So have a wonderful day and I will see you all on Thursday. Take care.
Thanks, Paul. Have a good one.
Take care.